And thank you all for coming and standing in a horrifically large queue. I know that it's a British pastime, but even still, it is very much appreciated. I have a bit of an interesting talk today, flying in the face of some of the InfoSec defaults, which I hope that you will, you'll appreciate. But I will cast a few caveats before I dive in. Firstly, as per usual, my presentation features a large number of different virtual machines, complex software setup, and continuous demonstrations, which means that the probability of it going smoothly is about 1 in 63,004. So when it fails miserably, some of you who've seen me present before will know I tend to sing something to distract people. Typically like the Canadian national anthem. I'm not Canadian, it's just a very distracting national anthem. But today it's probably going to be the Canadian national anthem translated into Klingon, because I found a Klingon translator online yesterday, and I'm just trying to use it for anything I can. Second little caveat, I am going to be doing a moderately technical presentation here. I'll explain why in just a moment. There are going to be some bits where some of you will get it. There'll be bits where you might be going, why is the Starship Enterprise attacking the Romulans on the screen? I have no idea what's going on. If that happens, give me a wave. I'll try and find other ways to explain it. It's quite normal for some of this stuff to not sink in the first time, but kind of hold on. All will become clear shortly. So, my starting premise is this. I spend a lot of time getting out into the world, talking to people at universities, at businesses, talking to the press. And I've noticed this interesting phenomena in our community that maybe some of you have observed as well. We are an astonishing group of technology users. I mean, the technology savvy of people today is unbelievable. But technology has become far more black box than ever before. Some of you in the room here will remember, when you had to edit autoexec.bat or config.sys to enable high mem so that you could play Commander Keen and get your Sound Blaster working, right? You remember that? Those were the days when computing was hard and you suffered until you could eventually get your game to work, which would be very exciting and moderately disappointing by today's standards. The problem is that with this abstraction comes a decrease in the understanding of low-level computing principles. Even very talented information security professionals are au fait with these concepts, but few have actually dug down into how these things work. Now, no shame on anyone in that position. You can be an immensely effective security researcher, a security professional, a defender, a pen tester, without that. But I find it a missed opportunity for interest and fun, but also a missed opportunity to be a better defender, forensic specialist, or penetration tester. I also find it important with the raft of interesting new vulnerabilities appearing in devices like, all the Internet of Things stuff, mobile platforms, and the like. So what I'd like to do is take you through, very briefly, a couple of threat trends, but I'd like to dive into the basics of exploitation. I'd like to show you a couple of simple examples before rushing on to a far more complex one. Now, this is a topic I could spend many days on any one small section of these slides. There is a lot here, and I'm going to attempt to cram 4 years of computer science degree plus some exploitation into about 34 minutes from now. Hold on to your seats. Now, exploitation, the basic notion is that through opening a file, through sending some malformed traffic to a network port, through some operation, we're able to trick a computer into abandoning the normal parameters of execution to do our bidding in some way. Now, that might just be crashing something, a denial of service. Or it may enable us more selective control to execute our own code, our own payload. Now, exploitation used to be wonderfully simple. Back in the days of smashing the stack for fun and profit, a seminal paper by Aleph 1 that some of you may remember, you could just go about, modifying memory, and there was very little to stop you. I have been quoted before as saying it, and I stand by it. A large portion of the security industry came into existence because Microsoft sucked. They made some horrible, horrible architecture decisions which allowed for interesting abuses of memory. However, whilst I used to say that, today, don't tell them, right? I have to be quite flattering. They actually have done a staggeringly good job of putting in place mitigations that make it hard to take software defects and turn them into exploits. It started around Windows XP SP2 with the likes of DEP. Now, many of you will have heard of DEP, Data Execution Prevention, the NX capabilities, the basic notion that we avoid sections of memory that should be used for storing data being executed. A bunch of other mechanisms in here as well. Safe SCH for prevention of abusive structured exception handling, for those of you that like Windows programming. Windows Vista, if you just take that column, if you shift it all to the right to Windows 7, because no one actually used Windows Vista, so technically these things appeared in Windows 7, address space layout randomization, a control that, again, many of you might have heard of. A seminal concept that you'll see when we come to exploitation very shortly is that you need to be able to overwrite select parts of memory in specific ways to point to addresses that contain your evil code. So the idea of ASLR, elegant and simple, why don't we just move these things around all the time so that instead of trying to hit that precise location again and again with reasonable odds, it becomes exceedingly difficult. Right? It's a bit like, the way I like to explain it, if we took this gentleman here and we gave him a dartboard, right? In Windows XP, all I've got to do is throw the dart and hit the center of the dartboard, and we win. With ASLR and Windows 7, improvements and beyond, we give him a couple of shots of vodka or Jaeger bombs. You like Jaeger bombs? Yes? Excellent. And, we get him to run around the room, and then we throw darts at him. But if we hit him or anything around, any of you guys with the darts, the program crashes. It's hard. Maybe we should be blindfolded as well. I don't know. So all these mitigations start to get in our way. Now, before we dive into actually doing some exploitation, there are some key concepts that we need to understand. Again, there's lots of architecture that I could review here, but I want to give you the quick and exciting version. When you look at memory on a computer today, these are, broadly speaking, the things that we are interested in. At the very top, on the CPU, we have something called the processor registers. Now, the registers are very, very small, finite in number, hard-coded variables. And they are used thousands and thousands and thousands of times per second to do unbelievably basic, beautiful manipulations like arithmetic and multiplication that comes together to draw every pixel on your screen, to process every keyboard press. It is actually quite beautiful and unbelievable when you think of the scale, as we'll see in a second. These processor registers are very, very fast and finite, as I've mentioned. Down below that, we have the processor cache. Typically a level 1 cache, a level 2 cache, sometimes a level 3. We need to think of these as a waterfall hierarchy in some ways. The processor register at the top is exceptionally fast. So if you think of it as a castle, right? Always good to have a castle metaphor in an InfoSec presentation, and at least 4 acronyms, which I'll make up in a minute. So the castle. The processor registers are in the throne room with the king. They're the CPU. It's very quick for the king to talk to the processor registers. The cache, being moderately large compared to the registers, is actually really quite slow by comparison, but quick compared to some of these other things down below. So the cache is where you get things like translation, look-aside, buffers, caching of instructions soon to be used. We need not concern ourselves too much with this for purposes of exploitation. RAM. RAM is really, really slow compared to the registers. So RAM is kind of like going out of the tower that the king is in into the courtyard, right, and going and sitting in the courtyard somewhere in a nice coffee shop. Pretty sure they didn't have those in castle times, but anyway, modern castle with coffee shops. Oh, that should be a thing. Anyway, it's pretty slow. Down below that again, we've got the disk. Really, really slow. This is where we get into things like paging and moving stuff out of memory into the disk. The disk is kind of like, I don't know, going to an airport and getting on a plane and flying to Australia, which they certainly didn't do when they, built castles. It's really, really far away. Most of what we're concerned with here is the manipulation of these registers, a few specific purpose ones, and some of the memory being held in RAM. A few specific registers for you. I won't go through all of these in a ton of detail, but a few that are very important to appreciate what we're going to do. EAX, RAX on a 64-bit system, the accumulator register. This is like the calculator of a computer. It's typically associated with arithmetic operations, integer multiplication, stuff like that. ECX, the count register. All of these are general purpose. They can be used by the computer for anything, but the convention is this is used for counting purposes, like the processing of loops. Now, here come the really important ones. ESP and EBP. The computer has a special area of memory called the stack, or procedure call stack in our specific case here. Now the stack is kind of like a scratch pad or a notepad for our computer. It grows up and down in a very structured, rigid way. So we start here in the stack, we allocate memory, we grow up, although perversely, the stack sits higher in memory and grows down. So when I talk about the stack growing and allocating memory, we're actually going to be subtracting memory to make that work. I know it's really, really weird. I'll show on a diagram in a minute. The stack is where we store information like parameters and variables that we're passing around, and it's also absolutely key to computers moving in and out of functions. So, here's a really simple explanation for you of execution, and we'll dive into our first example. Before I do that, is anyone bored yet? Good, okay. No one fell asleep just yet. All right. A computer executes instructions one after the other like a ladder. So it goes through doing the things that were compiled into our program until it finds a subroutine, a function. It then jumps off to some other location in memory. When we jump off to that other location in memory, we need a way to know how to get back to where we were before. What if we could hijack that process by overwriting that special construct in the stack, by changing something we shouldn't be able to? Modern exploitation involves a raft of very complex concepts, but we're going to go way back to really basic examples and build up. Here's our first one. This is a picture, a very, very simplified, rudimentary picture of an unbelievably terrible program that I have written that is purposefully insecure in memory. This program has two main things we're interested in. It has a buffer, size of 15, which can store some text. It's actually a char array for the more technically inclined. There's also an integer called pass stored nearby to this buffer. And this integer has a default value of 0. So let me jump over to this actual example here. Okay. Don't panic if you're not a programmer, if you don't read C. I'm going to step through this. It's actually not horrifically complicated. So what we're going to do first off is declare our buffer. Char buffer, size of 15. Int pass equals 0. So you see how that relates to the diagram I've just shown you. We're allocating those ready to be used. Down below, we're saying, what is the password? So we're just going to ask the user for a password, followed by a legendarily terrible function. The gets function is a banned, deprecated, terrible, terrible idea that is perfect for a basic explanation. What it does is it says to the user, please give me any user input. You type in your user input, and it dutifully writes it into the buffer that you specify. In this case, buff. Well, gets doesn't check how much user input you provide. I mean, why would that be important? So we start providing some data, and it writes it into that buffer. Let's have a look at what happens next. If strucomp buff awesome, again, not too hard to follow here. If the buffer contains awesome, and it matches awesome, right? If it matches, then we have our condition below. Else, the fail is strong with this one. So if it doesn't match, print the fail is strong. If it does, print password accepted and set the pass variable to 1. Everyone okay? Cool, nice and simple. Down below, we have our last little piece here. If pass, so if pass is not 0, that's shorthand for that, print secret awesome powers activated. Contrived example is contrived. Of course, in a real application, it probably does something more interesting than printing that. Although that would be cool if you found an actual program that did that. So, let's build this program and introduce the concept of why this is vulnerable. So we're just going to compile this. I'm going to turn off a bunch of security controls. There are exploit mitigations in this operating system that we don't want. So we've just built that program as a nice x86 executable, and it will by default be called a.out. So let's run a.out. What is the password? Well, of course, normally we don't have the source code, so we wouldn't know what it is. So we could type in something like that. The fail is strong with this one. If we type in awesome, secret powers activated. So let's introduce the most simple example of an exploit, a buffer overflow here. The bucket is this big, and right next to the bucket where we put that information is a little variable which, if we could change to anything other than 0, would give us secret powers. So we're going to overflow it. How do we do that? Unbelievably simple. We just put in a bunch of A's. Look at that. It's longer than 15 characters, so in memory it's gone along to the end of where it should be, overwritten that variable, and then the checker's gone, oh, well, pass is not equal to 0. It contains some portion of A's. Well, in that case, secret powers activated. So that simple notion of being able to go and overwrite the boundaries of data is what we're talking about. Everyone okay with that? Nice and simple. So let's upgrade this a bit, okay? Because unfortunately, you're not going to find examples like that for quite a long time. In order to dive into this, we need to understand a little bit more about how functions work on a computer. Now, this is an example, fairly arbitrary example, of a program which has been compiled, and we're looking at it in assembly. This shows us the low-level instructions that the computer is processing. It's a nice mnemonic representation of machine code. Up here at the beginning in our main here, we've got a series of instructions followed by a call to func X, highlighted here. So the program's going to execute these one by one until it hits that call. When it does, it's going to jump off to the memory address of func X, and it needs to know how to get back. The way that it does this is with the magical value, the return pointer. The return pointer is the address of the next instruction after the called function to be executed. Right? It's like setting a bookmark in your browser. So in the stack, we had a stack frame for main, and we've put this return pointer value just above it. ESP and EBP are two special purpose registers here. ESP always points, their general purpose registers being used specially, always points to the top of the stack. EBP points to the bottom of our present stack frame. Think of it like a bunch of fruit crates. When we put a new one on top, we move them to point to the top and the bottom of the fruit crate. When we remove that fruit crate, we move the top one down to the previous bottom and the other one down again. Using this, we grow up and down to enable us to move in and out of functions all the time. So let's jump into our function. We save the return pointer. There's another special value here, the saved frame pointer. This is recording the previous position of EBP. We're preserving where the stack frame was before so that we can get back afterwards. If we keep putting boxes on top and we don't know the dimensions of the previous ones, we're going to very quickly lose control and there'll be apples everywhere. Terrible metaphor. Okay. So, we're now ready to allocate some memory on the stack. We change EBP to be where ESP was before. And now we're going to allocate memory. In this case, the instruction subtracts 0x20, or 32 bytes, which makes us have a 32-byte buffer on the top. Now, some of you will have followed the technical details. Others, if you basically appreciate that it's growing up and down constantly, and we have this special return pointer construct that is used to get back to the code we were running before. All right, is anyone totally freaking out? All right, this is fun, isn't it? Cynical face. All right, so let's go and have a look at a real example of this and the opportunities that this presents us, okay? I will also point to a ton of resources if you want to learn more on this. As I say, it's a big topic. So I've got a program called Simple2. I'm just going to disable all of the security mitigations. These can be bypassed. I'd love to show them to you, but I would need like several hours rather than like 40 minutes. So we're going to keep it simple. We're going to run the Simple2 a.out program, and we're just going to put in a bunch of A's. Okay, nothing happened. We're going to use Python very quickly to generate a very large amount of data. 1,000 A's ought to do it. Okay. So we've generated 1,000 A's and we've fed it into this application. Segmentation fault. It's crashed. This is a good thing. We like crashes. So let's have a look at this program and see if we can figure out exactly what is happening. We're going to use GDB, nice little debugger, to analyze this guy. Okay. What I've done here is opened up GDB, and we're looking at the main function where the program starts execution. Now, lots and lots of scary stuff here for those of you that don't read assembly, but you might notice down here, does anyone see call check PW? I wonder what check PW could do. Maybe a check password function. Let's have a look at check PW. So there's a ton of different calls in here. I'm going to highlight the important bits. This call to get is likely where we're asking the user for input. Right, we just used that function before. What I'm going to do is set a breakpoint on the instruction just after this call to gets. A breakpoint lets us pause execution and look at the state of memory in the program to see what's going on as it executes. So we'll do a break, asterisk, memory address. Okay, so let's run our program and input my 1000 A's. As soon as we run it, we hit our breakpoint. In theory, this should be directly after we've input all that A's, and so we should be able to see them in memory. Can anyone remember the registers that were used to point to the top and the bottom of the stack frame? Yes, you said it, thank you. ESP. All right, so what we're going to do here is grab memory from this register's address, and we can see a bunch of 41s. Okay, in security you celebrate the small things, 41s, it's very exciting. 41 is hexadecimal ASCII equivalent code for the capital letter A. So that's our A's in memory. You see that? If we scroll down, there's tons and tons and tons of A's. Awesome. Well, let's have a little bit of a closer look at this program here and see if we can make something interesting happen. Right after our line, we have this LEA instruction. -0260, 608. This program is allocating about 608 bytes for us to be able to store the password. That's why it didn't crash when we just put in that small number of A's. But 1000 is much bigger. Let's also stroll down this program a little further and see if we spot anything else fun. I like this one. Always good when there's a function called granted in a program, isn't it? Very convenient. So let me show you how this starts to build together. We're going to take the memory address of the granted function over here, and let's see if we can actually build something a little nasty. I'm going to put this in the background, and we're going to do Python A times 612. I just need that address. Where is it? Granted. Okay, \x54 \x. Nope. If I make any errors, feel free to correct me. 85. 0804 855B. Little endian backwards. Okay. Let's run this again with our new attack. Excuse me. Scroll down to the bottom of our A's, and what you see here is the memory address I supplied. Well, this happens to be the perfect location of the return pointer. The return pointer, when it's called, is now going to point to this memory address instead, which means when I run our program, if we jump out here, it says access granted. Okay, that's not super exciting, is it? But think about that. We've overwritten something in memory that tells the CPU what code to run and redirected it to something else in memory. Well, making it run access granted isn't fun. Let's turn this into something real now. What we need is some shellcode, a payload. In this case, I've got some pre-prepared that listens on port 9999. We're going to make a backdoor. So, I always type exit eternally. Let me grab this little string and talk you through it. Looks terrifying. Actually, this string of hex here, I copied and pasted from Google. So not that terrifying, right? Never write your own shellcode. Always steal other people's. It's way easier. Followed by an address in memory where I think the shellcode is going to reside. So, let's see if we can make this thing work effectively. Let's set our breakpoint again on this memory address so we can see whether or not it's correct. Whoa, that was fun. By the way, afterwards you should come up and look at this laptop. It is the most ridiculous thing I've ever seen. It's like a foldable desktop with a full-size glowing red keyboard in it. It's completely stupid and brilliant. Okay, so now in memory, instead of our A's, we've got our shellcode. We scroll down, we've got all our A's, and this address, which is trying to point back up to the beginning of the shellcode that we provided. Let me just show you this again. Up to this address up here. Well, that's trying to precisely hit our friend over here with a dart. The probability of that working successfully is relatively minimal. Okay. So let's see if we can just improve the odds of this and complete this little exploit. And I'll start to wrap up with what next. The NOP instruction, 0x90. This tells the CPU to literally do nothing, which is wonderfully, wonderfully helpful. What we're going to do here is create a NOP sled, a large area of memory that just says do nothing. And what's beautiful about this large area of do nothing memory is that wherever the computer lands in it, like if I hit just outside the bullseye, like I hit his arm, we can slide down that until we hit our shellcode. It increases our probability of success significantly. So let's put in a \x90 times 200 there it is. Okay, so we've got 290s, but we need to make sure that return pointer ends up in exactly the same place. So we're going to go down to these A's and subtract 200 from our 528. It still equals the same size, right? 528 plus 200 plus the shellcode size gives us the 612 that we had before. Okay. So let's run this in GDB. Did I leave one in the background? I didn't. No. Like this. Set our breakpoint so we can see what's happening in memory. Here we go. And run with our file.txt. There are our 90 instructions, right? Now, if we scroll down, we'll see our shellcode and our return pointer down below. The only problem here is, whilst we put in this nice landing pad, we're still trying to perfectly hit the beginning of it. So, let's modify this address just a tad to give ourselves a bit more comfort. Let's aim around here, like 2A0, part way into those 90s. So here we go. Let's go back to our string and change this to A0. So we've got 90s, shellcode, A's, return pointer that points back to our 90s that drops into our shellcode. Okay. So what I've done is I've run the a.out program, and I've fed in this attack string file I've created. Now, it said access denied, but it hasn't crashed, right? It's just sitting there, waiting. What's happened is we've overwritten that return pointer, jumped back to our 90s, slid down the NOP chain, and hit our evil code. I'm going to open up another window here. Of course, we could do this from another computer if we wanted to, and look at the listening ports. Now, this is a little small, but some of you might be able to see the a.out program is listening on port 9999. Interesting. Let's connect to it. We have a backdoor. We connect to that port. That program is now allowing us to access the file system. We have a shell. So lots and lots of moving parts here, right? But what we've effectively done is, due to a software defect, poor programming, we've been able to overwrite an important part of the computer's memory that enables us to gain control of execution and supply our own code. Now, I'm sure lots and lots of you have heard of buffer overflows before. I'm sure lots of you follow all the nasty exploits in the news week to week. But it's probably the first time that many of you have actually stepped through one of these examples. Now, don't panic if you're feeling a little overwhelmed from that. I hope that you followed it at least at the concept level. There are tons and tons of great resources where you can go and learn more about this kind of stuff. You can step up from these basic examples into how to bypass DEP, how to get around ASLR. And actually, within a couple of weeks of concentrated learning and playing, you can be opening up parts of the Metasploit project and understanding how many of these attacks actually function. Many people are terrified by their first touch of exploitation. This stuff looks hard and scary. But if you read over it a few times, if you practice it, it's actually very logical and a lot of fun. This isn't just about becoming an exploit writer. It's not about, going and writing exploits and selling them for lots of money. This can be an invaluable skill to everyone in this room. As defenders, understanding the details of these attacks enables us to make better decisions about the controls we should run, enables us to be better at incident response and understanding how we were bypassed. As penetration testers, we can move beyond people that just use other people's tools into being able to craft and tailor things to succeed where others do not. That is the perfect emulation of our adversary today, of our attacker, who have these skills. And of course, the same goes for forensics, where when we know how we do it, we know where to look. I know this is a bit of a whirlwind tour in a short period of time, but it is a topic I'm extremely passionate about, and I think is extremely important for this group of people, for our industry, to have skilled individuals that get this stuff to some degree of detail so that we can kind of tackle cyber criminals who are eternally fantastic at sharing this information with each other and learning. I need to wrap up now. If you are interested in any more of these examples, the resources that I mentioned, places that you can go and pick up more of this stuff, do drop me a note on Twitter or find me on LinkedIn, email, fairly easy to find online. I really hope that you enjoyed this session. Let me know if you thought it was way too horrifically technical or actually quite good fun. And if you're confused about any aspects of it, please feel free to hit me up here. I'll be downstairs around the Sophos stand through the rest of the day. I'll even go through the example a few more times and later step through a modern exploit with ROP and Windows 7. Thank you very much for coming. Enjoy the rest of InfoSec. Thank you.